Welcome to this lecture series in group theory. In today's lecture, we will talk about the orthogonal group of the three-dimensional Euclidean space, namely R3, and give an explicit description of it, just like we had for the two-dimensional Euclidean plane, namely R2. So we have the orthogonal group of R2, which is defined like this. This is a cryptic way of saying it. This equation just says that the inner product is preserved. And we gave an explicit description of this guy by defining the notion of rotations and that of reflections, and showed that everything here is either a rotation or a reflection. The determinant 1 elements are rotations and the determinant -1 elements are reflections. And so let me not get into the details of what these definitions were. I am assuming that you're familiar with them. And after being done with this, we wanted to do the same thing for an arbitrary or an abstract two-dimensional real inner product space. Can we break down or explicitly describe the orthogonal group of an arbitrary two-dimensional real inner product space in terms of rotations and reflections? And we saw that there was a problem there, and to get around that problem, we had to have this notion of orientation of a real vector space. So we took a little linear algebraic detour in which we defined this concept, and I don't want to recall it. I'm assuming that you remember it, or you can go back to the lecture to refresh your memory. And then we also talked about the contracted orientation on a hyperplane of an oriented real inner product space, where the contraction was done with respect to a vector. So suppose I have a real inner product space V which has some orientation on it has been chosen, and we have a non-zero vector V. Then there is a natural orientation on the hyperplane which is perpendicular to V. How is that orientation defined? Well, you pick any ordered basis of the hyperplane H and append V to that basis. You will get an ordered basis of the ambient space V. If this ordered basis has the same orientation as the original orientation on the vector space V, you deem the chosen ordered basis of H as positively oriented, otherwise call it negatively oriented. And the positively oriented bases of the hyperplane H all have the same orientation, and the negative oriented ones or negatively oriented ones also have the same orientation, and the positively ones and the negatively ones have opposite orientations. All of that you can prove, as we showed. And so that is how you define an orientation on H. The bases which are positively oriented, the orientations of them is the contracted orientation on H with respect to the vector, this chosen non-zero vector V. So this vector V matters. If you replace V by -V, you will get the other orientation on H. So you fix a vector V, then the orientation on the ambient space contracts to get an orientation on this guy, and the procedure we just described. This terminology contracts is just, I don't know where it comes from, but this is how we say it. Okay, and after being done with all this business, we talked about the orthogonal group of the of any two-dimensional real inner product space, and we explicitly were able to describe it in terms of rotations and reflections, although I left the details as an exercise. All right, so let's get down to business. Some problems for practice. And now let us get started. So let us define rotation by an axis. So we have this space R3, and we have an axis chosen. Let's say this vector is V. So choose a non-zero vector V and take its span. That gives you an axis of rotation, and we want to define what is meant by rotating by theta about that axis. This is going to be a map from R3 to R3. We just want to explicitly write down what that map is. So the rotation of R3 along V by theta is defined as follows. All right, so first let V be the span of little v. So this one-dimensional subspace is V, and therefore we have its perp. V perp is a two-dimensional space, which is difficult for me to draw, but yeah, you can visualize. So define, or let, or even before that, equip V perp by the or with the contracted orientation, contraction of the standard orientation of R3, where the contraction is done by the vector V. Let me just say with respect to vector V, I hope you understand. So there is a standard orientation on R3, namely E1, E2, E3 in that order. This is an ordered basis having the standard orientation, and you contract that orientation to get an orientation on this hyperplane, which is the one that is perpendicular to this non-zero vector. Okay, and now let R theta be rotation by theta of V perp. V perp is an inner product space. Since it is a subspace of R3 and R3 is an inner product space, V perp is also an inner product space. So I should mention, but usually such things are not mentioned, that this has been equipped with the restricted inner product. There is an inner product on V, you can just restrict it to V perp, and therefore V perp is also an inner product space. Alright, so now since this is an oriented two-dimensional real inner product space, we can talk about rotations of it and let R theta be the rotation by theta. Very important that orientation was chosen. Otherwise, you cannot talk about rotations. Without an orientation, you cannot talk about rotations. Alright, and now finally, let R theta comma V, this be the linear map, or this be, let me just say it's a map, it will automatically be linear. So this is defined as or defined by writing, I'll just say defined as, the English may not be proper, R theta V of W plus W prime is equal to W plus R theta W prime, where or for all W in the span of V, or in the space in the space capital V, and W prime in V perp. So all of this writing should be consulted with this figure and understood geometrically. We have this hyperplane. We want to define this notion of rotation by theta along this axis, where it matters that this vector is known to us. If there is no vector here and I ask you what is meant by rotation about this axis, what would you say? Somebody might rotate it this way by theta and somebody else might rotate the other way by theta, right? I mean, which way do you rotate? Somebody who's looking this way on the axis may say, I will rotate by theta in this fashion. I don't know if you understand what I mean by this arrow. It's just anti-clockwise rotation in this perspective. But the other guy may look at the axis from this direction and then rotate anti-clockwise by theta in this direction. And those two things are different. Those two things are not the same. They are opposite in some sense. They cancel each other out if you apply them in succession. So which way do you do? So for that you need a vector. Once you choose a vector, now you can talk about rotation by theta unambiguously because of all this business. You orient this particular plane by contracting the ambient orientation with respect to the vector V. Now there is an orientation here and hence no ambiguity about rotation. So you just rotate this plane and keep everything on this axis fixed. That is exactly what this definition is. The things on the axis are fixed. They don't get disturbed. And the things perpendicular to the axis are rotated by theta. So all of this is very geometric in nature. There is no opaqueness about it. Completely transparent and natural and satisfactory definitions. All right, so that's the definition of rotation by theta along the vector V. And note that this thing belongs to the special orthogonal group of R3. Why is that? Well, first of all, it preserves inner products. That is very, very clear from this particular line. So that I leave you to check that it preserves inner products. It is important that W is in V and W prime is in V perp. So use that fact. All right. So the fact that it is an orthogonal group of R3 is very simple and very clear. Why is it in the special orthogonal group, namely why the determinant is 1? Well, if you choose an oriented basis of this hyperplane, then just form the matrix of R theta V with respect to this particular ordered basis. You can choose any basis you like in the universe, but if you just choose this particular ordered basis, you will see that the determinant of that matrix is 1, and that's it. So this is an exercise, but it's a particularly easy exercise. Okay, so these are natural elements of the special orthogonal group of R3. Rotation by axes, right? Okay, wonderful. Let's look at some examples. We have this particular axis, and rather we have also chosen a vector. As we said, when you're going to rotate about an axis, you need to mention a vector along that axis. So fix this vector E1, and we want to describe this particular rotation by theta about this oriented axis, if you like, and the matrix of that thing with respect to the standard basis. So when I don't write anything, meaning I have written matrix of a linear map, I didn't mention, but this was a linear map. R theta of V was a linear map, as you must have noticed. So the matrix of a linear map, when I don't write anything, then the basis with respect to which the matrix is formed is the standard basis. Euclidean spaces have a natural basis called the standard basis. So yeah, so the matrix of this particular thing with respect to the standard basis, as you can check, is going to be this matrix. Right? It is just going to disturb E2 and E3 and not E1. So E1 remains fixed, and E2 becomes this guy, E3 becomes that guy, and that is being captured here. All right, similarly, if you rotate about E2 by theta, you get this particular matrix, and if you rotate by theta about this particular oriented axis, namely by choosing E3 as your vector in the axis, then you get this matrix. Yeah, so I forgot to put a 0 here. There's a 0 here. So all of these things are very simple. Of course, you should definitely be sure that you get this. But more interestingly, suppose we do not have these very easy axes. Suppose we choose a rather complicated axis. Not the most complicated one, but sufficiently complicated. So our vector V is now lying in the plane of E2 and E3, but it is not along E2 or E3. It is tilted. So it is in this two-dimensional plane, the plane of E2 and E3, but it is tilted. And we would like to write down the matrix of R theta V with respect to the standard basis, right? That is one way to understand what the linear map really is. Just write down its matrix representation with respect to some nice basis. Okay, so that is what we are going to do in this particular slide. So to do that, note that E1 is orthogonal to the vector V because E1 is perpendicular to the plane in which V lies. So E1 is orthogonal to the vector V, and I have defined this another vector which I will call U. So this will be called little u, right? So U is a unit vector and V is also a unit vector. This vector V, I've chosen it as a unit vector. So alpha is which angle? Alpha is this angle. I should have mentioned that. This is alpha. Okay, so note that this basis E1, U and V is or has the standard orientation. Just follow the definition. Consider the linear map from R3 to R3, which takes E1 to E1, E2 to U, and E3 to V. And we know the description of E1, U, and V, everything very precisely. So you can compute the determinant of T. and you will find that the determinant is positive. In fact, the determinant will be 1. So this is certainly a correctly oriented, or the orientation of this particular ordered basis matches with the standard orientation on R3. Okay, and therefore, thus E1 comma U is an oriented basis, is a positively oriented basis, I will say, is positively oriented of V perp, or maybe more precisely I should write it like this, but I'll write V perp. So what am I trying to say? We have this vector V, and hence we have the plane orthogonal to it, which is what I'm denoting by this. And as the usual song we have sung, the standard orientation on R3 will get contracted by this vector to induce an orientation on this orthogonal plane. And by following the definitions, immediately we see that this particular basis is matching, or the orientation of this particular ordered basis of the hyperplane matches with the contracted orientation, simply because after appending V to this ordered basis, you get a basis whose orientation matches with the standard orientation. So this is positively oriented basis of the orthogonal plane. All right, great. And therefore, the matrix of R theta V with respect to this basis, this we can immediately therefore write down. This will be cos theta minus sine theta cos theta, and V remains undisturbed. Right? Just take this as an exercise. Nothing is going on. You have this hyperplane where this blue comma pink is the correct oriented basis. So E1 is getting rotated by theta, and this U is getting rotated by theta in that way. So it's just a copy of the Euclidean plane, E1, and this U is playing the role of E2. And this is the matrix that you get for the rotation of E1 and U, and that is just getting appended by this extra thing because this perpendicular dimension is undisturbed by the rotation. So this is an exercise, but I've explained it visually what it means. And now you know the matrix of this particular linear map with respect to this basis, whose description you explicitly know. You explicitly know what is E1, U, and V in terms of the standard basis. V is written this way in the standard basis, and U is written this way in the standard basis. So you can find out the matrix of this guy with respect to the standard basis by playing some linear algebra. And if you do that, which is again an exercise, you get this particular matrix. So the matrix of R theta V with respect to the standard basis is this horrible looking thing. Nice exercise, you should do it. We get some hands-on feeling about rotations, about axes. And we see that the matrices can look fairly complicated even though the geometric description is very simple. Okay. Now we want to also talk about reflections, just like we did for the orthogonal group of R2. So fix a two-dimensional subspace of R3. Then the reflection about H is defined as you can do it yourself, but I will write down the details. So it is defined as follows. This is the hyperplane H, or the two-dimensional subspace H. What we are going to do is we are going to define a linear map which fixes everything in the hyperplane. But if you take anything perpendicular to the hyperplane, it will flip it, meaning it will throw it on the other side. So that's the rough geometric meaning, and the proper definitions are these. Is defined as this particular map. This consumes a vector w plus w prime and outputs w minus w prime for all vectors w in the hyperplane and w prime in the perp of the hyperplane. Right? Very simple definition, and as in the case of rotations, you can easily see that this thing is in the orthogonal group. So that is also an exercise, that this guy is in the orthogonal group and its determinant is -1. To see that, just take any basis of the hyperplane and append that with anything orthogonal to it. You will immediately see that the determinant of SH with respect to this basis is -1. Okay? Yeah, so I should write here that this is what reflection about H is. But that is clear. Okay, so we have defined rotation about an axis by a fixed angle theta and reflections about hyperplanes. Both of these objects lie in the orthogonal group. The rotations lie in the special orthogonal group and the reflections do not lie in the special orthogonal group, but they lie in the orthogonal group. The determinant of rotations is 1, the determinant of reflections is -1. And now the agenda is to show that everything in the orthogonal group can be expressed by these two elementary transformations. Okay. Before we embark on the main business, we need to state two preparatory lemmas. They are very simple. Suppose you have a real inner product space V and we have an orthogonal transformation of it, meaning an element of the orthogonal group. Then every eigenvalue of it will be either 1 or -1. This is not to say that necessarily T will have some eigenvalue. It may have no eigenvalues. But if it has an eigenvalue, it will either be 1 or -1. So the reason is very simple. Suppose lambda is an eigenvalue. And suppose we have a non-zero vector such that T of V is lambda V. Now, by virtue of the fact that T is an orthogonal transformation, we get that TV dot TV is equal to V dot V. And that immediately gives us this equation, but this is same as saying, well, I will not write anything from this point on. This lambda and that lambda, they together conspire to become lambda square, and then you cancel off the V dot V from both sides. So you get lambda square is 1. Once you get lambda square is 1, you get lambda is either plus minus 1. That's it. So that's a very simple and general fact. And another thing I want to recall from linear algebra is that suppose we have an odd dimensional real vector space and we have a linear endomorphism of it, then it has an eigenvalue. There are perhaps many ways to do this, but one way is the following. You consider the characteristic polynomial of T. The degree of the characteristic polynomial is same as the dimension of the space in question. So it will be an odd degree real polynomial and hence will have a real root. Any odd degree real polynomial has a real root. This is a very simple argument by the intermediate value theorem in real analysis. And any root of the characteristic polynomial is an eigenvalue. In fact, the eigenvalues are precisely the roots of the characteristic polynomial where you're taking roots in the base field. So that's a proof of it, but there are other proofs. Okay. So now we want to talk about the Euler rotation theorem, which is a very beautiful and very interesting theorem. You can ask this or pose this as a puzzle to a high school student and he will understand what you're asking. But proving it is not so simple. It's a purely geometric theorem. Fix anything in the special orthogonal group of R3. We claim that it is a rotation about some axis. Right? It's a purely geometric fact that everything which preserves inner products and has determinant 1 is necessarily rotation about an axis. Also, you can get a handle on the axis, on the angle of rotation by means of this equation. This is very easy. Once we understand this part, this will be very easy. So, yeah. All right. So let's see why this is true. So first of all, since R3 is an odd dimensional real vector space, T has an eigenvalue. And since T is a special orthogonal transformation, the eigenvalue is either +1 or -1. Any special orthogonal transformation is in particular an orthogonal transformation. So any eigenvalue of T is either +1 or -1. And since R3 is odd, it has at least one eigenvalue. So fix an eigenvector, V be a non-zero vector, be non-zero, such that TV equals lambda V, where lambda is either +1 or -1, that we know. So there are two cases, either lambda is +1 or lambda is -1. Case 1, the easier case would be that lambda is equal to 1. So in which case T is fixing V. Right? If lambda is 1, then this equation is just saying that TV is equal to V, and one can draw a picture here. So this is V, and this is the hyperplane perpendicular to V. So the perp of V is this hyperplane H. Now, since determinant of T is 1, I want to claim that T restricted to H is a rotation. Even before we get there, since T is keeping this particular subspace invariant, and since T is an orthogonal transformation, it will also keep the perp of this subspace invariant, right? So this hyperplane is invariant under T. Okay, and our claim is, or whatever a fact is, or note, T restricted to H is a rotation, or has determinant 1, is a rotation. So all of these standard things apply. You have a orientation on R3, and the orientation on H is the contracted one. So now we can talk about rotations on H, and this is a claim that this is a rotation. To prove this claim, all we need to show is that the determinant of this guy is positive, or rather, in fact, 1. So why is it that this has determinant 1? Well, you pick any basis of H. In fact, you may pick an orthonormal basis, right? There are only two possibilities. Either this guy is a rotation or a reflection, because clearly this guy is an orthogonal transformation of H. T was preserving inner products in the entirety of the R3, and the inner product on H is the restricted inner product. So T will also preserve inner products of H. So it is clear that this guy is an orthogonal transformation of H. Maybe I will mention that. Make sure you understand this, but we claim that it is actually in the special orthogonal group of H. So to see that, fix any orthonormal basis here, call that V1, or let me call that maybe U1 and U2. So U1 comma U2 is an orthonormal basis, and you append that to V to get a basis of R3, and it is convenient to think of V as a unit vector, although that will not change anything. Now, what is the matrix of this guy, or rather the matrix of T looking like? Well, the matrix of T will look something like this. T of U1, we are making the matrix of T with respect to this particular ordered basis, U1, U2, and V. Right? So, the matrix will look something like this. You'll have some number here, and then a 0, because this entry corresponds to the component of TU1 along V. But that component is 0 because TU1 lies in H. So that will be the first column. The second column also will be some number, and 0, and the third column will be 0, 0, 1. So this is how the matrix will look. And the determinant of this part is same as the determinant of the entire matrix, right? And therefore, the determinant of this part is 1, because the determinant of the entire matrix is 1, courtesy T is a special orthogonal map. And lastly, what is this matrix? This is the matrix of this guy with respect to the basis U1 comma U2. So I've said a lot of things, but they are not very difficult to do by yourself. So I'll just mention that, in fact, this is in the special orthogonal group of H. Okay, and that finishes the proof of this theorem in this particular case when lambda is 1. Because once t restricted to h is in the special orthogonal group, it is going to be rotation by some angle, and that's exactly the definition of rotation about an axis, where the axis in this case is this particular line. That is the axis. So to end the thing, we are just saying that t is nothing but r theta v for some suitable theta. That's what t will be. So this is one case. The other case is that lambda is minus 1. Lambda is minus 1, so the picture will look something like this. This is v and tv is just the opposite. Think of v as a unit vector just for convenience. Now, by the same kind of reasoning, note that, first of all, t restricted to h is in the orthogonal group of h, where what is h? H, as usual, is the perp of v. So this is clear. We claim, in fact, that it is having determinant minus 1. Now, why is it minus 1? By the same reasoning. You pick an orthonormal basis here or any basis here, the matrix of t with respect to this, that, this ordered basis, the first one, the second one, and third one, will look something like some number 0, some number 0, and 0, 0, minus 1. The minus 1 comes because tv is minus v, right? And therefore, the determinant of this guy must also be minus 1, so that the determinant of t becomes 1. So the determinant of t restricted to h is minus 1, and hence this guy is a reflection of h. Once it is a reflection of h, it will fix a vector and it will invert a vector. So what I mean by that is, let me call this blue thing as u, or maybe I'll call this u1, and the pink thing as u2. So since t is a reflection of this guy, courtesy of these two deductions, it is going to be the reflection about some line. Let's say it is reflection about this line, and I've just chosen a vector on that line. So tu2 would be just minus u2. So this would be tu2. So what's going on? The whole of t, what is it doing? It is sending u2 to minus u2 and v to minus v. So you will see that it is actually rotation about this line by, I think, in this picture it looks like 270-degree rotation or something. Let me check. What does it look like? It is basically 180-degree rotation about this line, right? Because u2 is going to minus u2 and v is going to minus v. So about the blue line, the map t is just a rotation by 180 degrees. So in both cases, we see that t is a rotation about some axis. That's it. So that proves Euler rotation theorem, a very, very beautiful theorem. And as a consequence, suppose we have two hyperplanes in R3 and we have reflections about them, then if you compose those two things, you get a rotation. This is not geometrically challenging. If you just think about it a little bit, you will get why this is true. But if you just use this theorem, it is immediate, because what is the determinant of this guy? The determinant of this guy is 1, being the product of the determinants of these two maps. So the determinant is 1, and hence this guy is in the special orthogonal group of R3, and hence is the rotation about an axis. Okay. So that's that. And why is this thing true? Well, the reason is very simple. If theta is the angle of rotation, then the matrix of t with respect to a suitably chosen basis will look like cos theta minus sin theta, cos theta, 0, 0, 1, and 0, 0. So this is what the matrix will look like with respect to a suitably chosen basis. Once you have a rotation, this is all you can have. This is not the matrix with respect to the standard basis necessarily, but with respect to some suitably chosen orthonormal basis. I don't know where to put it. Whatever. Now, if you take the trace of this matrix, you get 2 cos theta plus 1. And trace of this matrix is same as trace of t. The trace of a linear transformation doesn't depend on which basis you choose to make the matrix. So the trace of t is necessarily this, and that's it. That's where this comes from. Okay. So that's that. And now finally, Euler reflection theorem, even though you will not find this particular phrase in literature, but what else will I call it? I'll just leave this as an exercise. The fact is that if you have an orthogonal transformation of R3 whose determinant is -1, then you can express T as this composite where SH is the reflection about H for some hyperplane H. I mean, there exists a hyperplane H such that T can be written this way, where SH is the reflection about H and RH is a rotation about the axis perpendicular to H. So this is an exercise, a very simple thing. If you understood the previous theorem, this is nothing. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.